How many of us?
Currently, there's 6 of us.
Okay, no problem. So okay, we'll just continue. Assalamualaikum warahmatullahi wabarakatuh. We'll continue for um we'll continue for the for what we have left last time. Do we have any question? Do you have any questions? Have you tried anything?
It was going okay.
Huh? Hey, this is not like a lecture room, yeah. I mean, where you can just sit and then listen to me. So it's more for the benefit of you and me. So that means you have to take part as well. Let's go- wait, stop, stop. What do you see?
All right.
Do you see any ISIS?
Yes, yes, yes.
Yes, yes.
Um, so I don't remember the oh I opened this already. Um, so last time we have evaluated and seen how we can use these thermodynamic models, and then we can see the interaction parameters available in each of the models, and which you can also fine tune according to your actual data. Yeah. Well, if you don't have any questions, that means I assume that you understand completely. So now, how calculation is done in process simulation software? So typically, typically, simulation software like this HYSYS or Symmetry or Aspen Plus, they work with what they call as sequential modular calculation. So what it means is that we have a stream, and then we add to it a block of calculation. So this can be um, a unit operation, for example, a valve or a pump or flash vessel or distillation column or reactor or whatever. Yeah, so it is like a block of calculation. So in this block of calculations, for example, yeah, if I put pump, so if this block is then the pump, you can see my cursor, right?
Yes.
So if this block is then a pump, while we have this is then the input. So what we can imagine is that we have these inputs or input feed situations. So we have the, for example, so this input like we have, so we have specified the conditions, by means of temperature and pressure in this case. And then we have the molar flow rates and then the compositions. So the compositions and then the mass flow rate and then the conditions. So we have the information available and ready in the stream. So this part is settled, and then comes if we want to put like a pump in this case. So this pump, we know that the equation for this pump is then this W, which is then the power of the pump, equals to the mass flow rates of the pump that goes through the pumps, and then the gravity acceleration, and then the head of the pump divided by the efficiency. So this is then typical of the pump calculations. So it's also like a delta P multiplied by the volumetric flow rate. So we have the delta P, how much pressure do we want to put or to give onto the fluid, or how much head do we want to increase the fluid, and then how much is then the fluid is going that we are going to pump, like in volumetric flow rate. So we need to know how much the fluid that's going to pump, which is then the flow rate of the fluid. And then we need to know how much we want to pump it, because for example, if we have this one at ATM, so do you want to pump it like 2 ATM or 3 or 4 or 15, 20, whatever. So we need to know that information. So in order to be able for us to solve these equations of the pump, yeah, that means we have already the fluid flow rate coming from the feed, but we don't know what the delta P is and then what the efficiency is. Yeah, in order for us to solve these equations. Yeah, we know the flow rate, which is coming from the feed, right? This is connected, so it will then take the flow rate value. But we don't know the delta P and then the efficiency. So in this case, if you look at these equations, so we have one equations only, and then we have only one known, right? The V, the volumetric flow rate, or in this case the M and G in this regard. But then we don't know what the delta P is, we don't know what the efficiency is, or in this case, we don't know what the head is, and we don't know what the efficiency is. Hence, we cannot calculate the W. So we have one equations, for example, in this case, and then we have only one unknown. Sorry, we have one equations, and then we have one known. So that means our degree of freedom is we have 1, 2, 3, 4, 4 variables, right? And then minus 1, which is then the equations. So we have 4 variables, W, delta P, V, and then efficiency. So we have 4 variables. And then we have one equations only, which is then W equals to delta P, V divided by efficiency. So that means 4 minus 1, that makes the degree of freedom is 3. So that means if you want to solve these equations, you need to put 3 more variables as the input. So we have already one, which is V. So that leave us with the remaining two, which is in this case you could put delta P and efficiency, or delta P and W, or W and efficiency. So 2 out of these, the remaining unknown 3 we have to put so that we can solve these equations. Okay, is this clear for now?
Yes.
Yeah, so in this case, for example, I put here, we know the fit situations, and then we need to put the head or the delta P, and then we need to put the equipment efficiency. So we have the fit flow rate, we put delta P, we put efficiency, hence we can calculate the W, which is then the outlet energy required. And then from this energy required, it will then calculate for us how much is then the outlet temperature, and then the remaining of the product situations. So let's put this into practice. So we have for example, this is just a dummy stream. So we have 75 degrees C. We're going to put the pump. So that means we need to make this in liquid form. So we have one ATM. Same flow rate, 1 ATM. And we have let's compare the let's go to our stream. So stream number 1, 25 degrees C, and we have 259.7 methanol and 2.5 water. So we have edit, edit, and then change to mole flow, and then 259, eh,
0.7.
257.9, right?
259.7.
25, very good, very good. 0.7, and then 2.5 water, and then no DME. Yeah. So, okay. So we have this molar flow rate, and then at these conditions, it is liquid methanol. Yeah, mostly methanol. And then yeah, we just put unique water in this particular case because we don't really care in that sense. So we have specified the feed, the stream, and then let's put a pump so that we understand it a little bit. So click and then click again, yeah, 2 times click, and then you can do one of the connections options. So drop down, and then you'll find stream number 1, and then stream number outlet is, then you could put like stream number 2, and then automatically appeared here, and then the energy stream is then the um, QP100, since the name of the pump is P100 by default. You can change it according to what you want, but in this particular case I'll just leave it as it is. Okay. So it gives, we have all the streams connections, inlets, outlets, and then the energy connections, yeah. And then this gives us unknown duty. Okay. So now my questions to you is that okay, we understand we have the inlet, and then we have to have also the outlet streams, right? That is very clear. That is very clear. But then why do I have to put this energy stream? Anybody knows? Why do I have to put the energy stream? Huh? Yeah, simply because if you want to calculate the pump, what's that thinking?
Energy.
Yeah, exactly. So right, you have to that pump has to be connected to an energy source, like in electricity, for example. So that means you need to know, if you know the duty, then you can calculate how big is then the cable that electrical people will do that, and then they will then connect it to the power grids, and then you can run the pump. Yeah, so it has to have an energy streams, and then we also see this from the equation, that this power or the energy is then the electric power, or the power that we need, which is then the power that we need to run the pump, which is then this stream. So that's why we need to have this energy stream. It is coming in, right? The arrow is pointing inward to the pump. That means we are supplying heat or supplying energy to the pump. So once we have all connections installed, and then it says to us, it gives us this, so it helps us a little bit to think. So unknown duty. So what it refers to is then this guy, this guy. Yeah, the unknown duty. So again, as I mentioned, that we have to specify 3 out of 4 variables. We have specified 1, which is then the volumetric flow rate, which you can see here. So we can go to worksheet, yeah, you can go to worksheet, and then we know, right? So this flow rate, it has been specified, right? So you can see the same number, yeah, in and out. So that means this part is settled. The flow rate is done. Yeah. So what is left is then the remaining 3. So we have to specify 2 out of 3. And then by default, it gives us, okay, you're going to specify the duty. Yes, you can, as we understand it now. But since you don't know, right? I mean, you just want to pump a liquid. You don't know how much duty. You need to know. Even you need to know the duty. Yeah, we want to know the duty. So that means we cannot input the heat flow, the Q here, because we simply don't know. But what we do know is that we want to pump it from 1 atm to, for example, 5 atm. Yeah, to 5, and then yeah, you could put atm, right? And then see, suddenly it goes to okay, it goes to green. So that means when you specify the flow, when you specify the outlet pressure, right? And then if you go back to the design, back to parameters, so this efficiency is already by default. Yeah, so if you remove this, and then nothing happens, right? So that means it shows to you that you indeed need pressure, or the delta P in this case, or pressure outlet in this case, and then you need to specify as well the adiabatic efficiency. So in this case, 75%, and then you get the results. And then this Q is then going to be calculated. Yeah. So if you want to do it the other way around, I don't want to know the efficiency. I don't know what the efficiency is, but I do know, yeah, from the electrical guy that I have, it costs us like 2 kilowatts. So you put 2 kilowatt over there, and then you will see a lower efficiency. You can see. So it was 1.5 at 75% efficiency, but now if you put 2 kilowatts, it means the efficiency of the pump is about 60%. Yeah, so either way, we need, you know that we have to specify. You can go back to worksheets. So you are specifying two, P and then the W, so that the efficiency is being calculated. Yeah. So I don't do this. So we typically have the 75% efficiency of the pump. So yeah, so this is one way to specify the pump. So we go to the design, we go to parameters here, we can specify whatever you want. Yeah. So blue means something that we specify ourselves. Adiabatic efficiency is already there by default, and then this delta P ratio and then duty is it's all black, so they are being calculated. How do we then change it? We go to the worksheet. If not, then you can just delete this. Delete. It doesn't want to be deleted. Delete. And then go back to design, and then you can put the numbers here. For example, delta P is then because you want to pump it at 5. Now we have 1, so that means 5 minus 1 is then 4. So 4 ATM. Yeah, voila. You get. So we have 2 blues, right? And then everything is calculated. Okay. You can specify it here, but then since you already put it there, that means this part you are not specifying anything. It is being calculated. Okay. So rating and the other curves, we can talk about it later, but now it is, in this case, we focus on the how this works. Okay, so we have specified feeds, we have specified the pump, and then we have the outlet of the pump being calculated. Okay, and then we put another unit operation the same way. So that means we have to specify whatever it is needed to be specified in this unit operations, and then the outlet stream will be calculated accordingly, and so on and so forth. So moving from left to right, from one block to the other block to the other block, or from one module to the other module to the next module to the next module, that's what they say as sequential modular calculation. Okay, because it's in module basis, and then it is sequential. Yeah, so we don't specify the stream here by any means. Yeah, you don't specify the stream here, you don't specify the streams. These streams are being calculated. Yeah, we have the input over here, we have the input in the equipment, and then the output of the equipment are being calculated. Okay, so this is then the basis for this sequential algorithm, sequential modular calculations. Yeah, in a more advanced session later on, you could do something, you can specify somewhere in between, but that is for the later case. Yeah, so that is for more advanced case. This is for the basic. This is what we have to understand as how to this sequential modular work. So do you have any question?
I do have a question.
Yes.
When we are designing a plan, and we don't have, say, the difference in pressure, but we do have the pump ratio, something like that. One of the data there. Is that okay to use that? I mean, from articles that they say that mostly pump or compressor can only achieve like 3 to 5 pressure ratio or something.
Yeah, fine. But then talking about compressor, we're talking about something different. Yeah, it's not about the because the limitation and that the power the limitation. What makes that limit is then the temperature outlet of the compressor of that fluid. Sorry, of the fluid that being compressed. So if the temperature is too high, and then you have we have in the compressor we have mechanical material limits for the the temperature limits on the seal of the pump, so that one of the mechanical stuff within the compressor. Sorry, so the upper limits that is allowed for that material to be exposed is somewhere about this 160, 170 degrees C or something, or maybe 180. I don't know. Yeah, depending on the mechanical seals, depending on the seals that they use. Yeah, so this vendor can give you that information, and based on that information, it says to us, like, for example, yeah, you are not allowed to have a fluid going through the compressor at a certain level, say 200 degree, yeah, just for simplicity. So that means you can increase your compression ratio while checking on the outlet temperature, yeah, in such a way that your outlet temperature of the compressor doesn't exceed that 200 degrees C. Okay,
Okay.
so let's
All right.
let's put this into practice. I don't know what we have here. Oh, we could also have this DME. What's the big deal? So we have, let's put this, yeah. So we have another stream, and then it is like a DME, because DME has a very low boiling temperature or very high vapor pressure. Let's put this DME pure, and then yeah, I don't know, 100 kilogram per hour, and then the pressure is 1 atm, and then the temperature is 25 degrees C, and then it is full vapor, yeah, full vapor. And if you like to know what is then uh, how do you call it, the dew point or the saturated vapor conditions of the DME at this pressure, what do we want? What do we need to input?
Vapor fraction.
Yeah, vapor fraction. So I want to have it like a saturated vapor. What is then the vapor fraction?
0.
I want to have saturated vapor.
1.
Ah, so it's 25 minus 25 degrees C. So if I put 0, what happens?
It's saturated liquid.
It's a liquid. So what is then the temperature?
And I don't know, 70 maybe.
Huh? Any more guess? Any better guess? Any better guess? No? Let's just put 0, yeah? Huh?
Oh, okay.
Why?
Oh, because it's pure.
Exactly. What is wrong with you?
Sorry.
Uh, so because it is pure, exactly. So if you go back, if you can still remember this guy, that guy.
Yeah,
So this is
yeah.
a pure, yeah, and this is 2 components, and then 3 components. I don't think we can draw it, but I think you get the idea of single component and then 2 components. Is there any questions? Oh, no question. Okay, so let's go back to business. So we 25 degrees C. So I mean that means this is already like a superheated vapor, yeah. So we want to compress this. Let's say go to compressor. This compressor, yeah. If you don't know, just hover, put the cursor over it, and then it will show you us the compressor. And then we could also how to connect this. I showed you already to do the drop down, but then in this case you could also do like you press control and then move the mouse the cursor over to the stream. So if it goes to here, it shows out, and you can just click it, yeah, and then drag it to this in. Sorry, in there. Okay, and then for the outlet you can also do the same, press control and then set it apply energy. This is logical input, this is logical output, this is Q, I don't know what this is, oil feed stream, and this should be the outlet. Yeah, there. Okay, and then what needs to be done? So we have inlet stream, outlet streams. Is there any other stream missing?
Energy.
Energy stream, exactly, because we need to connect this guy to a, yeah. So energy is then pointing into the compressor. That means we need to have energy to run the compressor. So it's helpful in a way, to help, to at least to, in your at your level, it's to confirm your understanding, yeah, and then it's also prevents like a stupid error or something. um okay, so the name is automatically there, so yeah, let's just put this qk. Okay, so because it's just also like compressing or putting pressure into the stream, so um, we are using the same equations, right? And then that means we need to put three independent variables. Flow rate is already there, so flow rate is 1. Yeah, flow rate is 1. And then we need to put either the power, the outlet pressure, or the pressure ratio, or the delta P, and the efficiency. So we go to parameters. Efficiency is automatically 75%. Yeah, in this case, adiabatic efficiency. You could also put polytropic efficiency, and then um, you could spec another delta P or pressure ratio, and yeah, in this case, just put pressure ratio. Yeah, put 2 or 3, enter, and then we have temperature. We check the temperature. Temperature is 80 degrees C, right? So it's quite cold, so I can compress more. Compress more. This is then from 1 to 3. Yeah? So I'll just delete because I don't want to click so many times. I'll just put it there. So if I compress to 3, it gets to this 80. If I compress to 4, it gets to 95. If I compress to 5, I can compress more. Goes to 106. So I can even compress more to 8, maybe. Space 131. So I can compress more to 10. 143. So in this case, we have already compression ratio of 10%, 10%, 10 times. And then we still don't limit. I mean, we now at this, okay, so in this case, it's 140, 150. So we are already at the typical border of temperature allowance for the compressor. So in this case, it's okay, right? So you could, in this particular case, you could compress it even to 10 times higher. So you are not limited to this 3 or 4 or whatever bullshit that you are hearing from the outside. Yeah. So because the basic is then to understand why they put that constraint. That is because there is a mechanical constraint on the current seal or material that they use within the compressor, and that's why they tend to compress or use compression ratio of 2, 3, depending on the or 4 even, depending on the gas compositions. But in this particular case, because we have a very special, in this case, chemical, so we can even stretch to 180, 10 times further. Yeah. But if your temperature is not 25 degrees C, but 50 degrees C, now you are not so okay with 10 times of compression ratio. So in this case, if we start at 50 degrees C, we have to reduce it to 9 atm, for example. atm. It's already at the higher limit as well. So so 8 bar, 8 atm, 159, still at the highest limit. So it's what matters is then this temperature limit, yeah, and then we need to check on the vendor, or you can just Google this yourself. The temperature allowable limit for a certain compressor or the compressor that you are using. So is this clear at this point in time?
Yes, yes. Very good.
Yeah. Okay. So we have the pump, and then we can put like a valve. Typically, yeah, typically they have a valve outstream of the pump just to regulate the flow rates there and over there. So again, you can see inlet. We key in the input data. We key in the necessary performance data in the pump, and then the outlet stream is being calculated, and then now this being the input for the next block, and then that means we need to key in what is then the necessary information in this particular block. So if you have a valve, so now let's test your mechanical fluid results, yeah, right? So
Okay.
yeah, you said you have passed this mechanical fluid, yeah, or fluid mechanic course. So we have the inlet outlet streams, and then this gives us, yeah. So this is too easy. So this gives us this unknown delta P. So that means you need to specify the unknown delta P is. But then as a side note, what is then the equation of a valve? Because without knowing what the equations for each of the union operation is, we don't know. We are not going to be able to find out how many is then the degree of freedom, right? Because for the pumps and compressor, we know that the equation is only this. This is the only equations for pump and compressor. Yeah.
Mhm.
And then we know we have proven ourselves that we have to put three variables to be able to calculate the other variable. But for valve, what is then the equation for valve? Anybody knows?
Uh,
Huh? Yeah, you
Q
can Google. You can Google it yourself.
for
Huh?
liquid, is this the control valve sizing formula?
Okay. What formula do you have in your mind?
Q equals to CV
And then
square root delta P.
square root delta P. Yeah, that is then roughly the equation for valve. So we have how many unknowns there?
CV value and delta
Yeah,
P.
and then
Delta P.
delta P, and then
Valve sizing.
no, no, sorry. How many equation? How many equation do we have? Only one. Yeah, that's
Yeah.
flow rate equals to CV times this square root of delta P. Typically, we have divided by the specific gravity. Um, so um, so we have like one equation, and then we have the flow rate, one variable, CV is another variable, delta P is another variable, and specific gravity is another variable. So we have four variables. So we have one equations, another four variables, and then that means we have to have like three variables specified. Okay.
Okay.
Yeah, we need to specify three variables. So let's go back to this. What do we have? We have the flow rates already. So that is then gone. And then, so what's missing is then the CV, delta P, and specific gravity. And then for, in this case, specific gravity is already there. Density is there. Yeah, density is over there. And then what is missing is then CV
Delta
and
P.
delta P. Yeah,
Mhm.
so that means we can either specify CV or specify the delta P. In this particular case, they say it's delta P, so that helps a little bit. Design parameters, so delta P. So just put delta P. So how much is then delta P you want to have? What is the net 5 bar? So delta
Why?
P typically, I don't know how much, half a bar. Yeah, so we put the half a bar, and then the outlet stream is I mean the equation is complete, and then the outlet stream is then being calculated. So we go to this. So alpha bar 506 minus 50 is 546. Yeah, so that's simple. And so we have done this, and then we can add another block, and then so on and so forth, so that we are okay. So any questions? Okay, never mind. Okay. I'm assuming that this Safik is asking about this, and then he understood that. Okay, never mind. Never mind. Um, okay, so any questions so far? Oh, more questions. Since well, we'll stick the flow. Yeah. In this current simulations, the valve does not restrict any flow. Yeah, it's just like destroying. It just destroy the pressure. It destroys the energy. You can also see that here. Have a click over there. So it has now we have like a 500 sorry 500, yeah, 506, and then now it has only like a 456 bar. So that amount of energy is then destroyed in this valve. What a bypass pipeline, do we need to have it in simulations? Depends. So what do you have in this? What do you want to simulate? Yeah. The question is then whether you need to have it or not depends on what do you want to simulate. So in this case, yeah, in this case, we just want to simulate the use of the a pump and the valve, and then if, for example, yeah, um, okay, because I think I need to explain to you one thing. So I haven't said this. So the simulations that we have now is what we know as the steady state. Yeah. So the steady state simulation. So what is coming in here, it has to come out there. So it's a mass balance. So what is coming out here, and then what is coming in here has to come out the same. So if this is then, for example, 262.2 kilomole per hour, and then this is also 262.2. This also has to be 262.2. Hence, this mass balance. Okay, the same goes with this 2.171. This is also 2.171. Yeah. There is no reactions whatsoever, so the mole balance is then equals to the mass balance. So in this particular case, it is a mass balance, steady state. So whatever happens here, it doesn't change with time. So if it changes with time, right? I mean, if you leave it like this and then you come back tomorrow, and it will still give you this 262.2, right? So it doesn't change with time. But if it changes with time, that means we are doing the dynamic simulation. So we will see that the flow rate can change. Yeah. And then if we open and close the valve, you will see that the flow rate will then going up and down as well, or accordingly. Okay. But in this particular case, we will do that dynamic later. In this particular case, we will do only steady states. So the steady states, remember that mass balance is then what you have to hold on to. Yeah. What comes in has to come out. Okay. So let's see if you understand this. We have a split here, so I have this stream, and then I want to split it. Pipe. I have a splitter. T. I put a splitter over here, and then the same way I do there, and then I do here, and I just do another one. Okay. Now we have stream number 5 coming into a T, yeah, where it will then be split it into two streams, stream number 6 and then stream number 7. So you will see that this is still like a light, and then that means it is not solved yet. This is like dark blue, they are soft, darkish, I don't know, it's got dark, so they are soft. And then it's also like light blue and it's not soft. Dark blue is soft. I think you know this already by now. So it needs to have a specifications, right? So what do you think the specification is to be able to solve this thing? Remember, this is steady state, so it has to be a mass balance at all time. So to be able to, okay, flow ratio. Yeah, what does it mean by flow ratio? You are right, yeah, correct, yeah, Shafiq. But then what does it mean in simple English? Flow ratio. So it's just the ratio between this flow and that flow, or this flow and that flow, any ratio. So you could also say, well, I want to have like 50% goes here. That means the other 50% will go there, or 30% goes here. That is 70% goes here. So how we do that is then just double click, and then it gives us this unknown splits, yeah, which is the answer that Shafiq gave just now. Go to parameters in the design tab. You go to parameters, and then yeah, which flow ratio, which one do you want to have more? For example, 0.4, and then obviously the other is then 0.6. So we'll see if 6 is then 0.4, 7 is then 0.6. That means so 262.2. So 40% will go to 0.6, and then 60% will go to 0.7. You can calculate this yourself, yeah, for your own convenience, and then also to increase your confidence, because by doing manual calculation yourself, and then you compare it with these commercial simulations, because these commercial simulations, they were developed by PhD and professors. So, and then they have been verified by years by practical community. So they hold the how do you call this, the highest level of certainty of correctness, yeah. And then you can compare your understanding with their results, yeah. So if your calculations match or close to what they give you, and then that means your understanding is okay, yeah. Okay, so now we have specified one. We have we have one specification filled in for the flow ratio. So what do you think the equations within this T should be? What is then the equations for this T?
M5 equal to M6 plus M7.
Yeah, exactly. So M5 equals to M6 plus M7. So we have the M5. So it's one equations, three variables. Yeah. So that means we have to specify two variables to make this equation solve. So you know the M5 already. So that leaves us with another one. And then we specify the flow ratio, or in this case, the flow rate of the 6. And then hence the flow rate of the 7 will be calculated automatically. Excellent. Okay. Any other questions? So far, so good.
So far, so good.
So far, so good. So that means you can move forward, and recycle. We'll talk about that later, and then we'll just try to do this, yeah, because recycle will come here. So we'll start with this stream number 1. It goes to the vessel V201. Yeah. This one I can just delete, yeah. Okay, including the pump. Delete. So this stream goes to VO1. So that VO1 is like a tank or a separator. Okay. So you can have separator or three-phase separator, or just simply a tank. But this tank is none other than the separator. tank, and then we'll see that this is V. I don't remember which V. V201. V201, and then what is coming in is then stream number 1, right? And then still we have to specify these two, yeah, because it's just like a separator. So we have downstream stream number 1, and then we have this stream without any name. You can put this 1A, and then there is another stream, but this stream we will have to neglect for the time being. Yeah, we'll have to neglect this. And then so this is stream 1A, and then the vapor stream, which is not shown here, right? The vapor is not shown here because this is then typically what they have in the plants. There is no vapor, there is no vapor flow rate with this methanol. Yeah, but for a typical process simulation to run, because we need to have the vapor stream. Yeah, later on you will see that vapor stream will be 0, but still you need to have that stream, otherwise it won't be calculated. And so this is one important difference as well from the simulations, and then what you see on the PFD or PNAD and what you see on the field. This is 1A as we know it, and then this you could put like 1B there. So once you specify 1B, it automatically calculated, right? There's nothing because not a product stream, but then you put 1B and it's automatically calculated. Okay, so energy here is optional. So that means if you put energy, that means you are like supplying heat or removing heat from the tank. But in this case, we don't want to do anything. What's come in will just come out, right? So parameters. So there is one actually when you do flash calculations, yeah, I think here I need to make an assignment for you. So try to make a flash calculation on your own, and then let me know how many degree of freedoms that you need. Yeah. Well, I'll give you the answer. You need 2 degree of freedoms. But then, so what is then that degree of freedoms? Number 1 is that the pressure. What is then the pressure in this vessel? So you can put, like in this case, delta P. Yeah. So if delta P is 0, that means the pressure here is then the same as pressure over there. So that's one. Then the second one is then the temperature. So pressure and temperature is then the 2 degree of freedoms that we need to have to be able to calculate the separator, the tank, or the flash calculation, basically. So we specify delta P or as 0. Yeah, so that's 1 degree of freedom. And then in this case, they specify also the delta P for the vapor outlet. So they specify delta P from here to there. So since delta P is the same, and then in this case it has a connection to the temperature here. So you could also see the it's the same way when we don't have this energy optional. So that means we don't specify any energy in or out. So this is automatically 0. So if this is automatically 0, so that means the temperature here, the temperature in this vessel is the same as the temperature in that vessel. The temperature is coming in. Yeah, temperature here is the same as the temperature coming in because we don't specify any energy. And then when we specify the delta P is 0, that means pressure here is the same as pressure there. So these two, pressure and temperature, for this tank or flash calculation to be able to be calculated, basically. Okay, so we go to worksheets, and then you will see. So stream 1A is then the liquid. So 262 coming in, it's fully liquid, right? And then the 1A is then coming as fully liquid with the same flow rate at 366, while 1B, it is fully vapor, but there's nothing there. All flow rates are 0. Yeah. So this is basically exactly the same as the as this guy.
Yeah.
Okay. So we have this, and then that, and then we have pump, right, which we have done. So we pump it, and then this pump is pump to O1AB, just to make it the same, yeah. Pump
201.
to 1AB. I don't know if you can, oh, you can do so. And then inlet is 1A, and then outlet is trim 2. Right? And then it needs the energy, so QP 201AB. Okay, so the same way, efficiency is by default, and then we want to pump it to. So how much do you want to pump it? So we have to see this stream number 2. Yeah, stream number 2. It's a 15.5 bar. So we can put it there. 15.5 bar. 15.5 space bar. That's the as you see, it says solve. Right. So we only need, in this particular case, we only need to have 2 inputs, as you understand it, the efficiency and in this particular case, the outlet pressure, because we know what the outlet pressure is. Yeah. What I often see from the students is because the students already have this stream table, and then it just like when they do this, and then they will then specify temperature here, specify pressure, and then they also specify the flow rate, right? So that's what they typically do, and then obviously this will not converge by doing so. But now, since you already understand what needs to be done, so and then now you understand why we have to put only delta P here and then the efficiency, and then it is solved. Yeah. Any questions so far? We have 7 more minutes, but I think I will just leave it here, and then here for your questions. So I would like you to do you have this do you have this Turton
Yes, we
appendix
do.
D? Yeah. So if you have this Turton appendix B, and then you have a HYSYS or ASPEN Plus or whatever installed, and you can just try to do it, yeah. And then if you find any problems, and then we can discuss it. Okay. So it's not going to be like me showing you this, and by the, yeah, even if when we have done this by the end of, for example, few weeks or few months, I don't know, if you don't do this yourself, you will not be able to do it. Yeah, that one I can guarantee you. If you don't do it yourself, you will not be able to do it, because this is a skill, right? You cannot swim without getting wet in the swimming pool. You are not going to be able to swim by reading book or by listening to a teacher or by watching videos. No. Yeah, you cannot do cycling. Yeah, you cannot ride your bicycle with only reading books, with only listening to or watching how to ride a bike. Yeah, you have to ride the bike, and then you have to fall, and you have to bleed, and then you have to come back up again, and then you have to ride the bike again. Yeah, that's how we do this, because that is a skill. It is a skill. It is not knowledge. Yeah, so what I suggest you to do, just go through this. So we have done it over here. So we know how to specify. At least now you know how to specify every block. Yeah, try to specify the heat exchanger block, the heat exchanger block, and then at least if you can do this, and then we can discuss intensely on the reactor next week. And then if you have any issue on here, and then we can discuss it as well.
All right.
Yeah.
Yeah.
Because you have to do it. Yeah. I mean. So because you have to face the problems, and then we will discuss the problem, and then only then you will understand how to solve it. If we don't find any problem, and then we don't know how to solve it, it's just by chance we get to no issue situation. Okay, so 4 more minutes. Any questions so far?
No from me.
Not from you. From you, Safik? No, Safik. How many of you? No?
There's 11.
11. Clear. Okay. Uh, for the rest, no, clear.
No, no, no for now.
Not for now. Okay. Okay. So it's a deal, yeah. Try to do this exchanger at least, or if you want to go, just go try to solve this. Yeah, just try to simulate this, yeah, until the end, right? And then we'll discuss. And then if all of you do this, each one of you independent, yeah, if you all do this independently, each one of you will hopefully face different issues, right?
Okay.
And then once we get to solve these 11 issues, for example, and then you have by then 11 no more knowledge, right?
All right.
Yeah. So
Okay.
thank you. Yeah, since there's no more questions, yeah. 3 moments, okay, fine. Thank you. So I wish you have a nice weekend, and then we'll talk to each other again next week. Yeah.
Yep.
Alright.
Thank you,
Thank
doctor.
you. Bye
Thank you,
bye.
Doctor.
All right. Bye.